skydiver has an approximate surface area of 0.5 meters squared. Now, that's implying that he's falling prone towards the earth. So his whole body is facing the ground. So he's not going head first or feet first. His whole body's prone. If he was going head first, the surface area would be much smaller, because it would just be his shoulder width times his chest width. So cross-sectional area in drag is whatever cross-sectional area is facing into the air. So what I want to know is the terminal speed of this skydiver before he opens his parachute. The only way to reach terminal speed is if drag is a factor. Okay, if there was absolutely no air resistance, no drag, then there would be no such thing as a terminal speed. Terminal speed could never be reached. So you have to have drag. So let's look at the picture here. My ever-exciting skydiver. What forces are acting on the skydiver as he's falling towards the earth? Drag. So drag and the force of gravity. There's no normal force. Why is there no normal force? He's not on a surface. You have to have a surface in order to have a normal force. So there's only two forces. There's drag and there's the force of gravity. So we only need to sum the forces in the y direction. Force of drag is up, force of gravity is down. So that equals the mass of our skydiver times the acceleration of our skydiver. Now we have an approximated equation for drag. 1/4 times the cross-sectional area times the speed squared. Force of gravity we know is mg. So this is our equation at the moment. 1/4 av squared minus mg is equal to ma. Notice mass doesn't cancel. So I'm going to have to give you a mass. Dang it. Let's say the mass of our skydiver, I don't know, 65 kilograms. Now, when the skydiver initially jumps out of the plane, there's drag horizontally on him because he's jumping out into the air, but vertically there's no drag yet. Because his speed, as he jumps out of the plane, vertical speed is 0. So the acceleration vertically, right as he jumps out of the plane, is 9.8 meters per second squared. You okay with that? So he starts falling. His speed gets bigger and bigger and bigger. But as his speed increases, this term, minus mg, becomes smaller. So his acceleration decreases from 9.8 meters per second squared downwards and gets smaller and smaller and smaller. What that means is he speeds up less and less. He's still speeding up, he just doesn't speed up as fast on his way down because of drag. At some point, the acceleration will become 0. Does it make sense for him to continue speeding up and end up with a positive acceleration? What would happen if the acceleration was positive? He'd slow down, slow down, slow down until eventually start to head back up towards the plane. That'd be kind of cool, yeah. But never seen it happen.
It'd be a great military.
Exactly. So the smallest the acceleration can be is 0. At some point, it's an ugly A, sorry. At some point, the acceleration will be 0. So what will that mean for the skydiver's motion if his acceleration is 0? That doesn't answer my question. What can you tell me about his motion if his acceleration is 0? It's a constant velocity. It cannot change. Which, yes, is why it's called terminal velocity. If acceleration is 0, velocity cannot change. So he will continue falling in a straight line at the same rate until he changes something about the drag. Say, opens the parachute. When he opens the parachute, that changes the cross-sectional area, which in turn decreases the terminal speed. So he slows down by a ton. So terminal velocity is the point when acceleration is 0. His velocity does not change anymore. It doesn't get bigger. Well, if acceleration is 0, then the drag force has to equal the force of gravity. If acceleration is 0, that term goes to 0, then the drag has to equal force of gravity. So his terminal speed, solving for v, we'll have the 4 over here with the mg. We'll divide by the area, square root it. That will be his terminal speed. So in the case of the numbers we have, for the mass is 65 kilograms, g is 9.8 meters per second squared. Cross-sectional area, we're estimating it to be about 0.5 meters squared. .4. Anyone else get that?
Yeah. Yes.
That's this in this particular case would be approximately 150, 160 miles per hour. Now, I was just guesstimating the cross-sectional area. I can't say how close that would actually be to a person. It's going to depend upon the person, too. A bigger person would have a bigger cross-sectional area. So. Now, this equation right here, this is only the terminal speed of a skydiver, something falling through the air. If you have, say, something going down an incline really, really fast, because there's people who are extreme skiers, for example, see how fast they can get going down a hill skiing, terminal speed would be different. This equation would not apply. The equation comes from setting up the free body diagram and solving for the speed. So it depends upon the picture. This particular equation is for this particular picture. Okay? Yes? At some point the acceleration will equal 0. It doesn't equal 0 the whole time. The acceleration at the very beginning his vertical speed is 0. So that term is 0 at that instant, so the acceleration is equal to negative g, so negative 9.8. But as speed increases and gets bigger and bigger, acceleration will get smaller and smaller, or closer and closer to 0 anyway. It has to stop at 0. It can't become positive.